Newton's three laws of motion describe how things move. Um, First off, we need to define what motion is. Motion is a change in position over time. Usually, the first law says that if an object's at rest, it's called the law of inertia. It's an object tends to keep on doing what it's already doing. If it's at rest, it wants to stay at rest, unless it's acted upon by an outside unbalanced force, like this soccer player's foot kicking the ball, applying a force to it, and that will make it move. Now, the second part of that is an object in motion, like this ball, wants to continue in motion. Again, unless acted upon by an outside force, such as the net, which stops it. When it hits the net, it applies a force to the ball stops. Now, in reality on Earth, there is a thing called friction that is usually in play here that will slow objects down. If you're in outer space and you were to kick this ball in outer space, it would continue on until it ran into a planet or a star or something like that, because there's no friction in space. However, on Earth, if you were to kick this ball and it was to roll on the ground, it would come to a stop due to the friction. So friction is a force. It's that outside unbalanced force that opposes motion. So this is the first law of motion. The second law of motion is the force equals mass times acceleration. And it's kind of easy to think about. If we had let me get my pen here. If I have force equals mass times acceleration, all it says is the bigger either one of these get on the right hand side, the more force I'm going to need. If I take, say I'm hitting this little golf ball, and then I take the same club and I apply the same swing and I hit this truck, well, of course the golf ball is going to go farther. That truck's not going to move at all. So the bigger the object gets, as this M gets bigger, the force needed is going to have to get bigger as well. Or if you want to make this acceleration get bigger, say instead of just tapping this ball lightly, I want to hit it way far. So if I want it to accelerate harder, I'm going to have to apply a larger force to it when I hit it. So as either one of these parts of the equation get larger, the force needed is going to have to get larger as well. And then the third law is the equal and opposite. For every action, there's an equal and opposite reaction. The force of the thrust coming out of the rocket down here is also, there's a force going down, but there's an equal force pushing upwards, and that's what actually makes the rocket fly. If you had two people running into each other, or if you throw a baseball off of a wall, the baseball hits the wall and applies a force, but the force is also applying a wall to the baseball, and that's what makes it bounce the other way. You can tie these all together. Look at this with like a cannon shooting a cannonball. The cannonball is obviously going to stay at rest inside the cannon until you apply a force to it. So that would be like Newton's first law up here. And then when it applies the force, there's also a force applied to the cannon itself. That's what gives it that recoil, makes the cannon kind of jump back as the cannonball is firing out the front side of it there. So that would be like the third law, equal and opposite. It's pushing the cannonball out the front side, but the cannon itself is also going backwards a little bit. Again, that little recoil. But the second law applies here because we're applying the same force to the cannon and the cannonball, but because the cannon is much larger than the cannonball, the acceleration isn't going to be as much. It goes backwards much less than the cannonball goes forward. And again, that goes back to the second equation, force equals mass times acceleration. You also see a lot of pictures like this up here in the top left corner. They have vector diagrams where they show the amount of force being applied, like 200 newtons here to the right, and we also have 175 newtons here to the left. The net force is the force that acts on the rope. If I have 200 newtons going to the right and 175 newtons going to the left, well, they kind of cancel each other out, but because there's a little bit more force going to the right, since there's 25 newtons going to the right, the net force of this rope will be 25 newtons to the right. The rope will move to the right. The dog on the right will win the tug of war, and it would be the same as if I applied a 25 Newton force to the right with nothing on the left-hand side. So this is called net force. You just look at the directions that the forces are being applied, and then the amount of force being applied. And since they're going in opposite directions here, we subtract 175 from this 200, and that leaves us with our 25 newtons there. If the dogs were going in the same direction, say they were both pulling to the right, and we had like maybe a cart over here or something, and one dog was pulling with 200 and the other dog was pulling with 175, they're kind of helping each other out. Well, then you would add them together. That would be the same as having, a really large dog that could pull at 375 newtons. He'd be able to pull about the same amount as these two dogs that are pulling at 200 and 175 newtons.